Hello, Mr. Simpson here with the video for 3.3 Development of Quantum Theory. So this is going to lead us into a conversation about electron configuration, which may be a little more familiar to you, but a lot of what you may have seen in the past with regards to electron configuration, 1s2, 2s2, 2p6, if any of that sounds familiar, is rooted in quantum theory and a set of quantum numbers. So we're going to cover that in this section. First, just here are the learning objectives as always, so take a minute to take note of those learning objectives. Next, while the work that we're going to do here with regards to electron configuration is going to seem very specific, we're still bound by what's known as the Heisenberg uncertainty principle. So you see that here. Fundamentally impossible to determine both the momentum and position of a particle at the same time, simultaneously. So while it'll seem like very specific when we get down to talking about energy levels and sublevels and orbitals, it is still impossible for us to know information about an electron at both its momentum and its position at the same time. Okay, just to reiterate a couple points here that we have already laid out with regards to electrons and energy, and that is first, they exist in discrete energy levels, but not between them. The energy of an electron in an atom is quantized, a specific amount of energy, and it can only be at certain values, as we saw, that it's going to exist in an energy level at a certain value, or absorb just the right amount of energy to jump to an excited state at a specific energy, and then give off that amount of energy to drop back down to another specific energy level. Okay, so we're going to talk about quantum numbers here and tie these into, like I said at the beginning, some of those electron configuration notes that you already may be familiar with. Okay, so the energy levels, 1, 2, 3, and so forth and so on, are labeled with the value n, and this is our principal quantum number. Generally speaking, the energy of an electron is greater for larger values of n. So as you can see in the diagram here, n equals 1 would be closest to the nucleus, and as I move out away from the nucleus, n equals 2, 3, 4, and so forth and so on. So the n is the principal quantum number, and we identify it with those integers 1, 2, 3, 4, and so forth. So this is one of three quantum numbers used to characterize an orbital. And over the next few minutes, I'm going to introduce the rest of them, and then we are going to work to identify the set of quantum numbers, 4 values for the different electrons in an atom. Just a reminder as we work through this that an atomic orbital is a general region in an atom that an electron is most probable to reside. Again, this is based on a probability of the location of the electrons. So in order to better understand or get rolling here, let's get to talking about the second quantum number, which is the angular momentum quantum number, represented by L. This defines the shape of the orbital, and whereas n equals the values 1, 2, 3, 4, and so forth, L equals a value from 0 to n minus 1. So if I had n equals 1 energy level, principal energy level, principal quantum number, then my L value possibility is just 0. Okay, because n minus 1 or 1 minus 1 would be 0. If I move a little further away and go to the second energy level, now I still have 0 is always a possibility, so my L values can equal 0 up to n minus 1. So 2 minus 1 would be 1. So I have 2 possibilities for a momentum quantum number here, L, angular momentum quantum number. Okay? Now, these L values represent the subshell or sublevels, and you may recall them being named or denoted with letters S, P, D, and F. You may remember that we said in the past, or when you worked with electron configuration in the past before, that the first energy level only has an S subshell. As we move further from the nucleus, the second energy level is a little larger. The second energy level has an S subshell and a P subshell. Head on to the third energy level, you're going to get an S subshell, you're going to get a P subshell, and you're going to get the D subshell for the first time. So you can see maybe how this relates to our quantum numbers here. When n equals 1, the L value can only be 0. So there's only one possible L value, 0. But when n equals 2, we have two possible L values, 0 and 1. And when n equals 3, I have three possible L values, 0 up to n minus 1. So 3 minus 1 is 2. So that means I have three possible values. I have L equals 0, 1, and 2. You may also then get to see here what's happening, and those values, when I say L equals 0, we're going to represent that with the S notation. L equals 1, that's going to be our P. L equals 2, that's going to be our D. So as I take a look here at this information, you can see what I'm talking about. So if my L value is 0, that's the S orbital. 1 is the P orbital, 2 is the D orbital, and 3 is the F orbital. So if I saw a notation like, they gave me principal quantum numbers that said 2, 0, when they list quantum numbers like that, it's always going to be in order. So that's the N value, that's the L value. So what I'm talking about here is an electron in the second energy level and in the S subshell. Second energy level, and when L equals 0, that's the S subshell. Okay, so let's continue. So I mentioned this refers to the shape. So the S subshell is spherical, P is dumbbell, and then D and F get a little more complicated. So there's this diagram you'll find in your textbooks, a little easier to see in the textbook or on the PowerPoint, but you can see the different shapes. There's the S. Here is our P in these three different planes, X, Y, and Z. And so you can take a look at these different shapes, but that's what the angular momentum quantum number is telling us. Next quantum number is the magnetic quantum number, ML. You'll see here that it specifies the orientation of the orbital in space. So you may remember this diagram from doing electron configurations. If you don't worry. We will be doing these orbital diagrams as a type of electron configuration in the next section. But you may remember these when we talked about a P subshell could hold 6 electrons. A P subshell could hold 6 electrons. The reason for that was because it had 3 orbitals. A D could hold 10 electrons, so each orbital can hold 2 electrons, which we'll see in our final quantum number in a second. But each orbital, you may recall, can hold 2 electrons. So if I have a D subshell that can hold 10 electrons, that means it has 5 orbitals. Okay, so the magnetic quantum number is going to equal negative L to L. Negative L to L. So if I had an L value of 1, L equals 1, that means my M sub L values are negative 1, 0, and 1. So if we think about an L value of 1, that tells me I have a P sublevel or subshell. I know that a P sublevel has 3 orbitals. Each can hold 2, so P can hold a total of 6 electrons. So now we're going to identify these orbitals as, with regards to their magnetic quantum number. So these orbitals would be identified as -1, 0, and 1. If I had an n value of 1, that means my L value is only 0, and that means my M sub L value would also then be only 0. Okay, so let's make sense out of this. My first energy level, the L value is 0 to n minus 1, so 1 minus 1 is 0, so I only have the possibility of an L value of 0. That means my S subshell. An S subshell can hold 2 electrons. Why can it hold 2 electrons? Well, because it only has one orbital. So as you can see in these S notations, it only has one orbital. So the value for the M sub L of that one orbital is just 0. Okay. So we're 3 quantum numbers in now, one more left to cover. Our last quantum number is the spin quantum number, ms. Well, the first 3, NL and ML, define the region of space where electrons located. This is a little something different. This describes the electron rotating or spinning. You may recall when we talked about how 2 electrons can fit into one orbital, 2 negatively charged particles located in one orbital, we talked about that in order to do that, they had to have opposite spin. So when we denoted that in an orbital diagram by having one of the arrows pointing up and one of the arrows representing electrons pointing down. Okay, so the M sub S values are either +0.5 or -0.5. Okay, so no ranges and things like we talked about in some of the other quantum numbers. It's just +0.5 or -0.5. And you can see if that electron is pointing up, spin up, it's going to be +0.5. If it's spin down, it's going to be -0.5. Remember, when we fill orbitals of equal energy, okay, we must put one electron in each orbital with spins parallel before we start to pair them up. We'll talk more about this in the next section when we really start doing electron configurations as well. Okay, when you put that all together, an electron is described completely by 4 quantum numbers, N, L, ML, MS. The Pauli exclusion principle, which may sound familiar to you, we'll talk about it again when we do electron configurations. No 2 electrons in the same atom can have exactly the same number of all 4 quantum numbers. You'll see that the first 3 could be the same, but the last quantum number, the spin quantum number, is what differentiates and makes sure that no 2 electrons have the same complete set of 4 quantum numbers. Okay, so we'll get plenty of practice on this with our homework and classwork, but just as to wrap it all up with a couple of examples before we get rolling here, hopefully this will help. So let's just pick an electron configuration here. Okay, so here's what I have. I've got 8 electrons described in this orbital diagram. If I just were to pick one, let me say this electron here, and wanted to describe it by listing its 4 quantum numbers. Okay, so you list them as they were listed above here, N, L, ML, MS, in that order with a comma between. So this electron is in the second energy level, so its N value is 2. It is in a P subshell, so if you recall, the L value for a P is 1. M sub L values are -L to L, so for my 3 orbitals here, they would be considered -1, 0, and 1. So the M sub L value is -1. And since that electron is pointing down, spin down, its MS value is -1/2. Okay, why don't I give you a second to try one. Identify for me the quantum numbers for that electron. You can go ahead and pause the video for a second and then turn it back. So again, this is the second energy level, so my N value is 2. This is an S subshell, so that means my L value is 0. If that L value is 0, the M sub L must also be 0, right? Because there's only one possible orbital in an S subshell. And then that electron is pointing up, so that is plus 1/2. All right, one more. Let's try one going the other way. What if I gave you a set of quantum numbers and asked you to identify which one of these electrons I was describing? So here are the quantum numbers I want to list. Two, 1, 0, negative 1/2. So why don't you take a second and point out the electron that is described by that set of quantum numbers. Hopefully you're saying that electron doesn't exist because the second energy level, the L value is 1, so that tells me I'm looking in the P subshell. I'm looking at the middle orbital because my M sub L value is 0, and I'm looking for the electron that is pointed spin down. And as you can see here, that electron is not listed here. So that electron does not exist in this particular example. I could correct this set of quantum numbers pretty easily by making this plus 1/2. That electron does exist. It is this positive 1 located spin up right here. Okay, so that wraps up this section. And as I've noted a few times, we'll get on in the next section to actually doing electron configurations. But for now, we're going to practice utilizing the quantum numbers.